Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why alien life might not use DNA, deoxyribonucleic acid, is the molecule of heredity for nearly all life on Earth. From bacteria to blue whales, from mushrooms to sequoia trees, every organism uses DNA to store genetic information, to pass traits from parents to offspring, and to direct the construction of proteins that build and maintain living cells. DNA's structure is elegant and famous, a double helix of two strands twisting around each other, each strand composed of a sugar phosphate backbone with 4 types of bases attached in sequences that encode genetic instructions. DNA seems so fundamental to life that it's easy to assume it must be universal, that any living thing anywhere in the universe would use DNA. But this assumption is almost certainly wrong. DNA is not the only molecule capable of storing and transmitting genetic information, and the specific chemistry that makes DNA work on Earth might not be optimal or even possible under different planetary conditions. To understand why alien life might not use DNA, we first need to understand what DNA actually does and what properties make it suitable for its role. DNA serves 3 critical functions. First, it stores information. The sequence of bases along the DNA strand encodes instructions for building proteins and regulating cellular processes. Second, it replicates. DNA can be copied with reasonable accuracy, allowing genetic information to be passed from one generation to the next. Third, it allows variation. Copying isn't perfect, and occasional errors introduce mutations that create the genetic diversity necessary for evolution. But DNA is not unique in performing these functions. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information, be copied, and undergo evolution despite having different chemical structures than DNA. These molecules use different sugars in their backbones, 3 O's instead of deoxyribose, locked nucleic acids with modified sugars, or even molecules with completely different backbone structures. These XNAs can form base pairs, store sequences of information, and be replicated by specialized enzymes. They demonstrate conclusively that DNA is not the only possible genetic molecule, merely the one that happened to work on Earth. The chemistry of DNA is optimized for Earth's conditions. DNA is stable in liquid water at temperatures roughly between 0 and 40 degrees Celsius, the temperature range where most Earth life operates. The hydrogen bonds holding the 2 strands together are strong enough to keep the double helix intact, but weak enough that the strands can be separated for copying. The sugar phosphate backbone is stable in water at neutral pH, but can be broken down by enzymes when necessary. The bases, adenine, thymine, guanine, and cytosine, are moderately stable molecules that can withstand normal cellular conditions but can be damaged by extreme heat, intense radiation, or strongly acidic or alkaline environments. On a planet with very different conditions, DNA might not function well or at all. Consider a world much hotter than Earth, perhaps a planet orbiting very close to its star, with surface temperatures exceeding 100 degrees Celsius, but with liquid water kept stable by extreme atmospheric pressure. At these elevated temperatures, DNA becomes increasingly unstable. The hydrogen bonds holding the 2 strands together weaken and break more easily. The chemical bonds in the bases and the backbone break down more rapidly. Organisms on such a world would need genetic molecules more heat-resistant than DNA, perhaps with stronger chemical bonds, more stable base structures, or completely different architectures that maintain integrity at high temperatures. Some Earth organisms that thrive in extreme heat have evolved DNA repair mechanisms that constantly fix damage to their genetic material, but there are limits to how hot DNA can tolerate. Beyond a certain temperature, the rate of damage exceeds the capacity of repair mechanisms to fix it. Alien life on a hot world might evolve an alternative genetic molecule with inherently greater thermal stability, perhaps using bases with stronger bonding, or sugars that resist thermal degradation, or entirely different building blocks that remain stable at temperatures where DNA would fall apart within seconds. At the opposite extreme, very cold worlds present different challenges. DNA becomes more rigid at low temperatures, making it harder to separate the strands for copying. The enzymes that copy DNA become less efficient or stop working entirely when too cold. Life on an extremely cold world, perhaps on a moon like Titan, where temperatures hover around -180 degrees Celsius, would need genetic molecules that remain flexible and functional at these frigid temperatures. The chemistry would necessarily be different from DNA, which was shaped by evolution to function in Earth's moderate temperature range. The solvent environment profoundly affects what genetic molecules are possible. DNA functions in liquid water, and its chemical properties are specifically suited to aqueous environments. The sugar phosphate backbone is hydrophilic, attracted to water, which helps keep DNA dissolved in cellular fluids. The bases are hydrophobic, repelled by water, which helps drive base pairing by pushing bases toward each other and away from the surrounding water. This balance creates DNA's structure and stability. In a different solvent, liquid methane, liquid ammonia, or something even more exotic, DNA's chemistry wouldn't work the same way. Water's polarity, its hydrogen bonding capacity, its ability to dissolve certain substances while excluding others. All these properties shape how DNA behaves. In liquid methane, a non-polar solvent, molecules that are hydrophobic in water might become soluble, while hydrophilic molecules might be insoluble. A genetic molecule designed for a methane-based solvent would need completely different chemical properties than DNA, perhaps with non-polar groups exposed to interact with the methane solvent, and polar groups hidden in the molecule's interior. The availability of raw materials constrains what genetic molecules can be built. DNA requires phosphorus, nitrogen, carbon, oxygen, and hydrogen. Phosphorus, though essential for DNA's backbone, is relatively rare in the universe compared to lighter elements. A planet poor in phosphorus might not be able to build DNA-like molecules and would need to evolve genetic systems based on more abundant elements. Perhaps silicon could replace phosphorus in the backbone, or sulfur could play a role, or arsenate, a chemical similar to phosphate, might substitute. Though experiments with arsenate-based DNA on Earth showed it's much less stable than normal DNA. The 4-base system used by DNA, adenine, thymine, guanine, and cytosine, is not the only possible coding scheme. RNA, DNA's chemical cousin, uses uracil instead of thymine, demonstrating that the specific bases aren't fixed. In principle, genetic molecules could use 3 bases, or 6, or even more. More bases would allow more information to be encoded in shorter sequences. With 4 bases, each position in the sequence can encode 2 bits of information, but with 8 bases, each position could encode 3 bits. An alien genetic system might use more or fewer bases depending on what works best with its chemistry. Some scientists have even created expanded genetic alphabets, DNA-like molecules with additional base pairs beyond the natural 4. These synthetic genetic systems can store more information per unit length than natural DNA and can be copied by modified enzymes. The existence of these expanded alphabets demonstrates that the 4-base system is not uniquely optimal, but rather reflects the specific chemistry that evolved on Earth. Alien life might independently evolve genetic systems with different numbers of bases encoding information in different ways. The structure of the genetic molecule might differ radically from DNA's double helix. DNA forms a helix because of how the bases pair and how the sugar-phosphate backbone bends. But other structures are possible. Some XNAs form helices with different geometries, left-handed instead of right-handed, wider or narrower than DNA, with more or fewer base pairs per helical turn. Some synthetic genetic molecules don't form helices at all, but adopt completely different three-dimensional structures. An alien genetic molecule might be a triple helix, a quadruple helix, a ladder without a twist, or some topology we haven't imagined. The copying mechanism might also differ. DNA is copied by enzymes called polymerases that move along the DNA strand, reading the sequence and creating a complementary new strand. This process requires a complex molecular machinery that evolution has refined over billions of years on Earth. Alien life might evolve completely different copying mechanisms, perhaps catalytic RNA-like molecules that copy themselves without protein enzymes, or inorganic crystals that template the formation of complementary structures, or even copying processes that don't involve template-directed synthesis at all, but rather some form of self-assembly guided by the genetic molecule structure. The rate of mutation, how often copying errors occur, affects evolution's pace. DNA polymerases on Earth make errors at a rate of roughly 1 mistake per billion bases, copied for the most accurate enzymes, though rates vary. This error rate is low enough to preserve genetic information across generations, but high enough to generate the variation necessary for evolution. Alien genetic systems might have very different error rates. A system with much lower error rates would evolve more slowly, potentially making adaptation difficult. A system with higher error rates might generate variation faster, but risk genetic information degradation. The optimal error rate depends on generation time, selection pressure, and environmental stability. RNA represents an alternative genetic molecule that exists on Earth and might have preceded DNA in evolution. RNA can store information, catalyze chemical reactions, and replicate all functions DNA cannot perform alone. The RNA world hypothesis proposes that early life used RNA as both genetic material and catalytic molecule before DNA and proteins evolved. An alien world might develop life that remains in an RNA world-like state, never evolving DNA, or might evolve RNA into forms more sophisticated than anything on Earth, creating genetic systems based on elaborate RNA structures rather than DNA. Some scientists have speculated about non-molecular genetic systems. Perhaps information could be stored in the crystal structure of inorganic minerals, with patterns of inclusions, defects, or layering encoding information that could be replicated when crystals grow and form templates for new crystals. Or perhaps information could be stored in magnetic domains in iron-rich minerals, with the orientation of magnetic fields encoding genetic instructions. These ideas are highly speculative and face enormous challenges. How would such systems be read and translated into functional structures? But they illustrate that genetic information storage might not require organic molecules at all. The universality of certain aspects of information storage might transcend specific chemistry. Any genetic system, whether based on DNA, XNA, RNA, or something entirely different, must be able to store discrete, sequential information, symbols arranged in order that can be read and interpreted. This is fundamentally a problem of information theory rather than chemistry. The specific physical substrate that stores the information might be less important than the information itself, and the mechanisms for reading, copying, and translating it into functional structures. If we ever detect alien life, determining its genetic system would be among the first questions we'd want to answer. If alien life uses DNA with the same 4 bases and same genetic code as Earth life, it would suggest either that DNA is universally optimal, unlikely given all the possible alternatives, or that Earth life and alien life share a common origin, perhaps through panspermia. the hypothesis that life can spread between worlds via meteorites or comets. Finding alien life with completely different genetic molecules would confirm that life can independently originate using different chemistry, revealing that DNA is merely one solution among many to the problem of heredity. The genetic code, the mapping between base sequences and amino acids, might also differ. Earth's genetic code is nearly universal across all life, with 3 base sequences called codons specifying which amino acid to insert when building proteins. But the specific assignment of codons to amino acids appears somewhat arbitrary. There's nothing inherent in the chemistry of the codon UUU that demands it code for the amino acid phenylalanine rather than some other amino acid. The code seems to be a frozen accident. Once it was established early in evolution, changing it would be catastrophic because it would alter the meaning of every gene, so it became locked in place. Alien life would likely evolve a completely different genetic code, with different codon assignments, and possibly even a different codon length. 2 base codons, or 4 base codons, or variable length codons. Why alien life might not use DNA comes down to DNA being a solution specific to Earth's conditions: liquid water at moderate temperatures, specific pH ranges, availability of particular elements, and the accidents of chemical evolution that occurred during life's origin on our world. Different conditions would favour different molecules, and even similar conditions might allow evolution to discover different solutions. DNA is remarkable and elegant, but it's not magic or inevitable. It's chemistry, sophisticated, evolved chemistry that works beautifully on Earth, but that represents just one possible answer to the fundamental question of how to store, copy, and transmit genetic information across generations. Across the universe, life might employ countless different genetic systems, each one adapted to its world's unique conditions, each one encoding information and enabling heredity through different molecular mechanisms, proving that while the principle of heredity might be universal wherever life exists, the specific molecular machinery implementing that heredity can vary as widely as the diversity of worlds themselves, with DNA being merely Earth's particular solution to the universal challenge of passing genetic information from parent to offspring through the generations. Why one side of the moon always faces Earth. If you look at the moon on any clear night, you'll see the same familiar pattern of light and dark regions, the features we call the man in the moon or the rabbit, depending on cultural interpretation. This pattern never changes. The same side of the moon perpetually faces Earth. There is no natural rotation of the moon that would show us different faces throughout the month. Ancient astronomers noticed this peculiarity thousands of years ago, and for centuries it seemed like a remarkable coincidence. Why would the moon's rotation period exactly match its orbital period around Earth, both taking about 27 days? The answer involves no coincidence at all, but rather a physical process called tidal locking that inevitably synchronizes the rotation and orbit of any moon close enough to its planet. Tidal locking occurs because of tidal forces, the same forces that create ocean tides on Earth. Tidal forces arise because gravity weakens with distance. The side of Earth facing the moon experiences slightly stronger gravitational pull from the moon than Earth's center does, and Earth's center experiences slightly stronger pull than the side facing away from the moon. This difference in gravitational strength across Earth's diameter creates the tidal force that stretches Earth slightly, raising bulges on both the near and far sides. The same process works in reverse. Earth's gravity creates tidal bulges on the moon, though without oceans these bulges are in the solid rock itself. The moon is slightly elongated, stretched along the Earth-Moon line, with the long axis about 20 meters longer than the short axis. If the moon rotates relative to Earth, these bulges try to rotate with the moon, but Earth's gravity pulls on the bulges, trying to keep them aligned with Earth. Imagine the moon rotating slightly faster than once per orbit. As it rotates, the tidal bulge tries to rotate ahead of the Earth-Moon line. But Earth's gravity pulls more strongly on the closer bulge, creating a torque that opposes the rotation, slowing the moon down. This gravitational torque acts like friction, steadily dissipating the moon's rotational energy. The energy doesn't disappear. It converts into heat through internal friction as the moon flexes slightly, warming the lunar interior by tiny amounts. Over millions of years, this process slows the moon's rotation until it matches the orbital period. Once synchronized, the same side always faces Earth. The tidal bulges align perfectly with the Earth-Moon line, and there's no more torque trying to change the rotation. This is the state the moon reached long ago. The moon is tidally locked to Earth, rotating once on its axis in exactly the same time it takes to orbit Earth once, both periods equal to about 27.3 days. From the moon's perspective, Earth hangs nearly motionless in the lunar sky, drifting slightly back and forth due to libration, small oscillations caused by the moon's slightly elliptical orbit and tilted axis, but never rising or setting. If you stood on the near side of the moon, Earth would always be visible. If you stood on the far side, Earth would never be visible, hence why that hemisphere is sometimes mistakenly called the dark side, though it receives just as much sunlight as the near side. The timescale for tidal locking depends on several factors. Larger tidal forces lock a moon more quickly, closer moons experience stronger tidal forces and lock faster than distant moons. Moons with more internal friction, perhaps from molten interiors, dissipate energy more efficiently and lock faster. For the moon, calculations suggest that tidal locking occurred relatively early in the moon's history, within the first 100 million years or less after its formation. By the time complex life evolved on Earth, the moon had already been showing the same face toward our planet for billions of years. Tidal locking doesn't just affect the moon, it's common throughout the solar system. Most major moons are tidally locked to their planets. Jupiter's 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, all show the same faces to Jupiter. Saturn's large moon Titan is locked. Neptune's moon Triton is locked. In fact, of all the major moons in the solar system, almost everyone is tidally locked to its planet, because they've had billions of years for tidal forces to synchronize their rotations. Some moons have been locked into more complex rotations through resonances with other moons. Mercury, though not a moon, is locked in a 3-to-2 resonance with the Sun. It rotates 3 times for every 2 orbits, a more complex tidal lock. Pluto and its large moon Charon are mutually tidally locked. Each shows the same face to the other always. Pluto rotates once per orbit, and Charon orbits once per Pluto's rotation, so they're perpetually facing each other across their orbit. The tidal locking process also affects Earth, though much more slowly because Earth is more massive than the Moon. The Moon raises tidal bulges on Earth, primarily in Earth's oceans, creating the familiar ocean tides. Earth rotates faster than the Moon orbits. A day is 24 hours, while the Moon's orbital period is about 27 days. This means Earth's rotation carries the tidal bulges ahead of the Moon's position. The bulge closer to the Moon is slightly ahead of the direct Earth-Moon line, and the Moon's gravity pulls backward on this bulge, creating a torque that slows Earth's rotation. This effect is measurable. Earth's rotation is slowing by about 2 milliseconds per century. Days are getting gradually longer as Earth loses rotational angular momentum. The angular momentum doesn't vanish, it's transferred to the Moon's orbit. As Earth slows down, the Moon speeds up slightly in its orbit, and a faster orbital speed means the Moon moves to a higher orbit. The Moon is currently receding from Earth at about 3.8 centimeters per year, precisely measured by bouncing laser beams off retroreflectors left on the lunar surface by Apollo astronauts. This process has been operating throughout Earth's history. Early in Earth's history, when the moon was much closer, days were much shorter, perhaps only 5 or 6 hours long, and the month was shorter too. Ancient corals and other organisms that leave daily growth rings provide evidence for shorter days in the distant past. Going forward, the process will continue. In the far future, if given enough time, tens of billions of years, Earth's rotation would eventually slow to match the moon's orbital period. At that point, Earth would be tidally locked to the moon, just as the moon is now locked to Earth, with the same face of Earth always facing the moon. However, this will never happen because the sun will evolve into a red giant in about 5 billion years, long before Earth could become tidally locked to the moon. The expanding sun will engulf the inner solar system, making the question of Earth's rotation academic at best. The tidal locking of the moon has significant consequences for lunar exploration and observation. The far side of the moon remained completely unknown until spacecraft flew around it. The Soviet Luna 3 probe in 1959 captured the first images of the far side, revealing a surface surprisingly different from the near side. The far side has many more craters and far fewer of the dark volcanic plains called Maria that dominate the near side's appearance. This asymmetry likely relates to the moon's tidal locking. The near side experienced more volcanic activity, possibly because Earth's gravity affected the moon's internal structure and thermal evolution. Communication with spacecraft on the lunar far side requires relay satellites because direct signals cannot reach Earth from there. China's Chang'e 4 mission, which landed on the far side in 2019, used a relay satellite positioned beyond the moon to maintain communication. Future lunar bases on the far side would face this same communication challenge, requiring either relay satellites or cables running over the lunar surface to the near side. Tidal locking affects more than just moons. Many exoplanets discovered orbiting close to their stars are likely tidally locked, with one hemisphere permanently facing the star in daylight, while the other remains in eternal darkness. These planets, particularly those orbiting red dwarf stars, where the habitable zone is very close to the star, would have extreme temperature contrasts between their day and night sides. Understanding how atmospheres redistribute heat on tidally locked planets is crucial for assessing their potential habitability. The fact that one side of the moon always faces Earth is not a lucky accident, but the inevitable result of physical forces operating over immense timescales. Every moon close enough to its planet will eventually lock, synchronizing its rotation to its orbit. The moon reached this state billions of years ago, and it will remain locked for the remaining lifetime of the Earth-Moon system. The same face that witnessed Earth's formation, the rise of life, the age of dinosaurs, and the emergence of humanity will continue watching Earth for billions of years to come, held in place not by chance but by the patient, inexorable work of tidal forces that have shaped orbital dynamics since the solar system formed, creating the familiar face we see in the night sky every month, unchanging and eternal from our human perspective, yet itself the product of changes stretching across geological deep time. What's left after a star explodes? When a massive star reaches the end of its life and explodes in a supernova, the detonation is one of the most violent events in the universe, releasing in a few seconds as much energy as the sun will radiate over its entire 10 billion year lifetime. The outer layers of the star are blasted into space at thousands of kilometers per second, creating an expanding shell of hot gas enriched with newly forged elements. But the explosion doesn't simply obliterate the star. At the center of the expanding debris, something remains, a compact, incredibly dense object created from the collapsed core. What gets left behind depends on the mass of that core and determines whether the remnant becomes a neutron star, a pulsar, a magnetar, a black hole, or in rare cases, nothing at all. The immediate aftermath of a core collapse supernova leaves behind a proto-neutron star, an extremely hot, dense ball of neutrons about 20 to 30 kilometers in diameter, containing between 1.4 and about 3 solar masses compressed into a volume smaller than a city. The temperature at birth exceeds 100 billion degrees Celsius, making it one of the hottest objects in the universe. Over the next 10 to 20 seconds, the proto-neutron star cools by emitting enormous numbers of neutrinos, ghostly particles that barely interact with matter but carry away 99% of the supernova's energy. As the proto-neutron star cools and stabilizes over minutes to days, it becomes a neutron star, a stellar remnant held up against further collapse by neutron degeneracy pressure, the quantum mechanical resistance of neutrons being compressed too closely together. The density is extraordinary, about 500 million tons per cubic centimetre, comparable to compressing all of humanity into a volume the size of a sugar cube. A neutron star is essentially a single gigantic atomic nucleus, held together by gravity rather than the strong nuclear force. The structure of a neutron star is layered and complex. At the surface lies a thin atmosphere, only centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, about a kilometer thick, where matter exists as a crystalline lattice of atomic nuclei, extremely neutron-rich nuclei unlike any found on Earth, embedded in a sea of electrons. These nuclei become increasingly neutron-rich with depth, containing far more neutrons than protons. Deeper still, at the interface between outer and inner crust, neutrons begin to drip out of nuclei, creating a neutron superfluid that coexists with the nuclear lattice. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever, a quantum mechanical phenomenon that can only occur at extremely low temperatures or extremely high densities. In neutron stars, despite the enormous temperatures by human standards, the density is so extreme that superfluidity occurs. The inner crust, extending to about 10 kilometers depth, consists of increasingly exotic arrangements of nuclei and superfluid neutrons. Computer simulations predict that nuclei might arrange into cylindrical rods, flat plates, or even more complex three-dimensional structures, nicknamed nuclear pasta, because of their resemblance to spaghetti, lasagna, and other pasta shapes. This nuclear pasta might be the strongest material in the universe, billions of times stronger than steel. Below the crust lies the outer core, where nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain electrical neutrality. Both the neutrons and protons exist in superfluid and superconducting states respectively. The protons form a superconductor, where electrical currents can flow without resistance. This region makes up the bulk of the neutron star's mass and extends to perhaps 10 to 12 kilometers from the center. At the very center, in the inner core, where densities exceed that of atomic nuclei by factors of 2 to 10, matter might exist in states never observed in laboratories. Neutrons themselves might break down into their constituent quarks, creating quark matter or strange quark matter. Other exotic particles predicted by quantum chromodynamics, the theory describing the strong nuclear force, might appear, including hyperons, kaons, or pion condensates. The exact nature of matter at these densities remains one of the great unsolved problems in physics, accessible only through observations of neutron stars and theoretical calculations. Many neutron stars are born rotating rapidly, spinning tens or hundreds of times per second, inheriting and concentrating the angular momentum of the massive star's core as it collapsed. If the neutron star's magnetic field is tilted relative to its rotation axis, which is common, the neutron star becomes a pulsar. The magnetic field, enormously compressed and amplified during the collapse, can reach strengths of 1 trillion times. Earth's magnetic field. Charged particles accelerated along magnetic field lines near the poles emit beams of radiation that sweep through space like a cosmic lighthouse. When one of these beams sweeps across Earth, we detect a pulse, hence the name pulsar. The pulses arrive with extraordinary regularity. The Crab pulsar, formed in the supernova observed in 1054 AD, rotates 30 times per second. The fastest pulsar known, PSRJ 1748-2446 AD, discovered in 2006, rotates 716 times per second. So fast that its equator is moving at about 24% of the speed of light. At these rotation rates, the neutron star bulges significantly at its equator but holds together through its tremendous gravitational binding and the strength of neutron-degenerate matter. Pulsars gradually slow down over millions of years as their magnetic fields radiate energy and carry away angular momentum. The rate of slowdown reveals the pulsar's age and magnetic field strength. Young pulsars like the Crab slow down noticeably over human timescales. The Crab's rotation period increases by about 38 nanoseconds per day. Old pulsars slow down much more gradually and eventually become too slow to generate detectable pulses, though the neutron star continues existing as a dark, cooling ember. Some neutron stars are born with even stronger magnetic fields, up to 1,000 times more intense than typical pulsars, reaching magnetic field strengths of 10 to the 15th Gauss. These objects are called magnetars, and they're the strongest magnets in the universe. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms become elongated into needle-like shapes. The magnetic field stores so much energy that magnetars occasionally undergo starquakes, sudden rearrangements of the neutron star's crust that release tremendous bursts of X-rays and gamma rays. The magnetar SGR 1806-20 released a giant flare in 2004 that briefly saturated instruments across the solar system despite being 50,000 light-years away. Not all neutron stars become pulsars. If the magnetic field happens to be nearly aligned with the rotation axis, the beams don't sweep across our line of sight, and we don't see pulses. These objects, often called radio-quiet neutron stars, or simply isolated neutron stars, are much harder to detect. They can only be found through their thermal emission. They're hot enough, at temperatures of a few million degrees, to emit X-rays. The Hubble Space Telescope and X-ray observatories have identified several dozen of these isolated neutron stars, though many more certainly exist undetected. Binary systems where a neutron star has a companion star create unique situations. If the companion is a normal star and the orbit is close enough, the neutron star's gravity can pull material from the companion. This material spirals inward through an accretion disk, heating to millions of degrees and emitting intense X-rays before crashing onto the neutron star's surface. These X-ray binaries can be incredibly luminous, sometimes outshining entire galaxies in X-rays. The infalling material also carries angular momentum, spinning up the neutron star. Over millions of years, an old, slow-spinning pulsar can be recycled into a millisecond pulsar, rotating hundreds of times per second, rejuvenated by mass transfer from its companion. When two neutron stars orbit each other, they form a binary neutron star system. Objects like the Hulse-Taylor binary, discovered by Russell Hulse and Joseph Taylor in 1974, which earned them the 1993 Nobel Prize in Physics. These systems emit gravitational waves, ripples in spacetime that carry away orbital energy. As they lose energy, the neutron stars spiral closer together. Eventually, after millions or billions of years, they merge in a catastrophic collision. The merger produces intense gravitational waves, events that LIGO and other gravitational wave observatories have detected. along with a kilonova, a spectacular explosion that creates heavy elements like gold and platinum through rapid neutron capture. The merger of two neutron stars can produce different outcomes depending on the total mass. If the combined mass is below about 2.2 to 2.9 solar masses, the exact threshold remains uncertain. The merger might create a more massive neutron star, though one that's likely unstable and will soon collapse. If the total mass exceeds this threshold, the merger immediately creates a black hole, with no stable neutron star phase at all. The LIGO detection in 2017, designated GW170817, appears to have created either a hypermassive neutron star that collapsed within seconds or a black hole directly. If the collapsing core of a supernova exceeds about 2.2 to 3 solar masses, again, the exact threshold depends on the poorly known equation of state of nuclear matter. Neutron degeneracy pressure cannot halt the collapse. Nothing known in physics can support the core against its own gravity. The collapse continues, compressing matter to infinite density at a point called a singularity, surrounded by an event horizon from which nothing can escape. The stellar remnant becomes a black hole. The supernova explosion might proceed normally, leaving a black hole at the center of the expanding debris. Or if the core is sufficiently massive, the collapse might be so catastrophic that it swallows the infalling material before an explosion can develop, creating a black hole with little or no visible supernova, a so-called failed supernova. Stellar mass black holes created from supernova typically contain 5 to perhaps 20 solar masses. They're invisible except through their gravitational effects and the radiation from material falling into them. In X-ray binary systems, black holes reveal themselves through the extremely energetic X-rays emitted by infalling material, distinguishable from neutron star systems by the absence of pulsations and by the inferred mass. Anything above 3 solar masses cannot be a neutron star and must be a black hole. Some supernova types leave nothing behind at all. Pair instability supernova occur in extremely massive stars, those with initial masses exceeding about 130 solar masses. In the cores of these giants, temperatures and photon energies become so extreme that gamma-ray photons spontaneously convert into electron-positron pairs. This pair production removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is obliterated. No neutron star, no black hole, just an expanding cloud of debris. These explosions were more common in the early universe, when stars could grow more massive due to lower metallicity, but they might still occur in regions with primordial composition. The observable supernova remnant, the expanding shell of gas and dust, evolves over thousands to tens of thousands of years. Initially, the blast wave plows through the surrounding interstellar medium at thousands of kilometers per second, creating a hot, shock-heated region. The Crab Nebula, the remnant of the 1054 supernova, is still expanding at about 1,500 kilometers per second. The pulsar at its center powers the nebula's glow, creating a wind of relativistic particles that illuminate the expanding gas. Older supernova remnants like the Cygnus Loop, about 10,000 years old, have expanded to hundreds of light years across. The blast wave has slowed to tens of kilometers per second, and the shock is transitioning from adiabatic expansion, where the remnant retains its heat, to radiative expansion, where the shocked gas cools and radiates energy away, creating the delicate filaments visible in optical and X-ray images. Eventually, after perhaps 100,000 years, the remnant merges with the surrounding interstellar medium, its expansion slowing to match the general motion of gas in the galaxy. The enriched material, oxygen, carbon, silicon, iron, and other elements forged in the star and the explosion, mixes into interstellar clouds. These enriched clouds eventually collapse to form new generations of stars and planets, incorporating the elements created by the previous stellar generation. Every atom of oxygen you breathe, every atom of carbon in your body, was created in a star and dispersed by a supernova, later incorporated into the molecular cloud from which the Sun and Earth formed. What's left after a star explodes depends on the fine details of mass, composition, rotation, and magnetic fields, whether the core becomes a neutron star or black hole, whether the neutron star becomes an observable pulsar or remains radio quiet, whether the magnetic field is ordinary or reaches magnetar strength. Each stellar death creates a unique remnant, a compact object encoding in its properties the history of the parent star and the violence of its death, objects that will persist for trillions of years after the last stars have formed, cooling slowly in the expanding universe, monuments to stellar death that simultaneously mark endings and beginnings in the grand cycle of cosmic recycling. Why some objects in space are heavier than others. When you hold a rock in one hand and a piece of styrofoam the same size in the other, the difference is immediately obvious. The rock is heavier. This difference comes from density, the amount of mass packed into a given volume. The same principle operates throughout the universe, but on cosmic scales, the variations in density become far more extreme than anything we encounter in daily life. Understanding why some objects in space are heavier than others means understanding how matter behaves under different conditions of temperature, pressure, and gravity, and how the history of an object determines what it's made of, and how tightly that material is packed together. Start with the simplest objects in space, clouds of gas in the interstellar medium. These clouds are extraordinarily diffuse, containing perhaps only a few atoms per cubic centimetre. In comparison, the air you breathe contains about 25 billion molecules per cubic centimetre. The density of interstellar gas is so low that the best vacuum we can create on Earth is still millions of times denser. These gas clouds have mass, sometimes thousands or even millions of times the mass of the Sun, but it's spread across such enormous volumes that the density is essentially zero by any terrestrial standard. Planets show a wide range of densities depending on their composition and formation history. The gas giants Jupiter and Saturn are primarily hydrogen and helium, the lightest elements. Jupiter's average density is about 1.3 grams per cubic centimetre, only slightly denser than water. Saturn is even less dense at 0.7 grams per cubic centimetre. It would float in a bathtub if you could find one large enough. This low density reflects their composition, dominated by the lightest elements in the universe, compressed by their own gravity, but not enough to create extremely high densities. The rocky planets of the inner solar system are much denser. Earth has an average density of 5.5 grams per cubic centimetre, about 4 times denser than Jupiter, despite being much smaller. This difference comes from composition. Earth is made primarily of rock and metal, silicates in the mantle and crust, iron and nickel in the core. These materials are intrinsically denser than hydrogen and helium. Silicon, oxygen, magnesium, and iron atoms are much more massive than hydrogen atoms, and when they bond together into minerals and metals, they pack together more tightly than gases can. Mercury, the innermost planet, is even denser than Earth at 5.4 grams per cubic centimetre, despite being much smaller. For a small planet, this density is surprisingly high, and it tells us that Mercury must have an unusually large iron core relative to its size. The leading theory, developed by planetary scientists studying how planets form, suggests that a massive impact early in Mercury's history stripped away much of its rocky mantle, leaving behind a planet that's mostly iron core, with only a thin shell of rock surrounding it. The iron, being much denser than rock, gives Mercury its high density. White dwarfs represent a dramatic jump in density. These are the remnants of stars like the Sun after they have exhausted their nuclear fuel and shed their outer layers. What remains is the core, compressed by gravity but supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. A white dwarf packs roughly the mass of the Sun into a sphere about the size of Earth, creating densities around 1 million grams per cubic centimeter, or 1 metric ton per cubic centimeter. A teaspoon of white dwarf material would weigh about 5 tons on Earth. This represents matter compressed to the point where atomic nuclei are essentially touching, with electrons flowing between them in a degenerate electron gas. Subrahmanyan Chandrasekhar calculated in the 1930s that there's a maximum mass for white dwarfs, about 1.4 times the Sun's mass, now called the Chandrasekhar limit. Above this mass, electron degeneracy pressure cannot support the star against its own gravity, and further collapse occurs. This calculation, which earned Chandrasekhar the Nobel Prize decades later, explained why some stellar remnants become something even denser than white dwarfs. Neutron stars take density to an even more extreme level. When a massive star's core collapses in a supernova, if the core's mass exceeds the Chandrasekhar limits, but is below about 3 solar masses, it compresses beyond the point where electron degeneracy can support it. The electrons are forced into the protons, combining through inverse beta decay to form neutrons. The result is a neutron star, a sphere about 12 miles across containing 1 to 2 solar masses. The density at a neutron star's center reaches about 500 million to perhaps a billion tons per cubic centimeter. This is comparable to the density inside an atomic nucleus, meaning a neutron star is essentially a single gigantic nucleus held together by gravity rather than the strong nuclear force. At these densities, matter behaves in ways impossible to replicate in laboratories. The neutrons exist in a superfluid state with zero viscosity. The outer crust is a crystalline lattice of neutron-rich nuclei. Deeper down, neutrons drip out of nuclei and flow freely. At the very center, densities might exceed that of atomic nuclei, and matter might transition into exotic states, quark-gluon plasma, where neutrons dissolve into their constituent quarks, or other forms of matter predicted by quantum chromodynamics, but never observed. Black holes represent the ultimate extreme of density, though their density is somewhat paradoxical. The matter that forms a black hole collapses to a singularity, a point of infinite density, where general relativity predicts that space-time curvature becomes infinite. The singularity is hidden behind the event horizon, and we can meaningfully talk about the average density within the event horizon. For stellar mass black holes formed from collapsed stars, this average density is extraordinarily high, but for supermassive black holes containing millions or billions of solar masses, the event horizon is so large that the average density within it can be quite low, sometimes less than water for the largest black holes. This doesn't mean the black hole's interior is actually that density, just that if you calculated density by dividing total mass by the volume enclosed by the event horizon, you would get that number. The density variations we observe in the universe reflect the different physical processes that create and shape cosmic objects. Gas clouds have low density because gravity hasn't compressed them significantly. Thermal pressure from their temperature balances gravity, maintaining their diffuse state. Planets have intermediate densities determined by their composition, which depends on where they formed in the protoplanetary disk and what materials were available. Rocky planets formed close to their stars where it was too hot for ices to condense, while gas giants formed farther out, where ices could exist and helped build massive cores that captured hydrogen and helium. Stellar remnants have high densities because they are supported not by thermal pressure, but by quantum mechanical degeneracy pressure. As physicist Wolfgang Pauli explained in formulating the exclusion principle in 1925, fermions, particles like electrons and neutrons, cannot occupy identical quantum states. When you try to compress them, they resist because there are no available quantum states for them to occupy. This quantum pressure can support matter to much higher densities than thermal pressure can, but only up to certain limits determined by the mass and the type of fermion providing the support. Temperature also affects density. Hot gas is less dense than cold gas at the same pressure because the particles move faster and push outward more strongly. This is why hot air rises. It's less dense than the cooler air around it. In space, hot gas in the coronas of stars or in galaxy clusters has lower density than cooler gas in molecular clouds, even when both regions have similar pressures. The Sun's core, where temperatures reach 27 million degrees Fahrenheit, has a density of about 150 grams per cubic centimetre, dense by terrestrial standards, but far less dense than a white dwarf, even though the Sun's core is much hotter. The difference is that the Sun is supported by thermal pressure from ongoing nuclear fusion, while a white dwarf is supported by electron degeneracy pressure after fusion has ceased. Composition fundamentally determines the density any object can achieve under given conditions. Hydrogen, the lightest and most abundant element, naturally produces lower density objects than heavier elements. This is why gas giants, primarily hydrogen, are less dense than rocky planets made of silicon, oxygen, and iron. But composition interacts with pressure in complex ways. Under the extreme pressures inside Jupiter, hydrogen is compressed into a metallic state, denser than solid hydrogen would be under normal conditions, though still less dense than rock or metal. The formation history of an object determines both its composition and its density. Early in the solar system's formation, different materials condensed at different temperatures as the protoplanetary disk cooled. Close to the Sun, only metals and rocks could condense. These became the rocky planets. Farther out, where temperatures were lower, water ice could condense, providing additional solid material that helped build larger cores. These larger cores could then capture hydrogen and helium gas before the solar wind swept it away, forming gas giants. Farther still, at the coldest reaches, methane and nitrogen ices could condense, contributing to objects like Pluto and other Kuiper Belt objects. The history of compression matters too. Jupiter's core is thought to be compressed rock and ice, squeezed by the weight of the hydrogen and helium above it, to pressures millions of times Earth's atmospheric pressure. Under these conditions, materials that started as ordinary rock and ice are compressed to much higher densities, possibly exceeding even the density of iron under normal conditions. The exact state of matter under such extreme pressures remains uncertain. Laboratory experiments can replicate some of these conditions, but not the combination of extreme pressure, temperature, and scale found in giant planet interiors. Rotation affects density distributions within objects. A rapidly spinning object experiences centrifugal forces that cause it to bulge at the equator and flatten at the poles. This changes the density distribution, making the equatorial regions less dense and the polar regions denser. Saturn, spinning rapidly and composed largely of fluid, shows a noticeable oblate shape. Its equatorial diameter is about 10% larger than its polar diameter. Neutron stars spinning hundreds of times per second bulge significantly at their equators, altering their density distributions and affecting how they emit radiation. Throughout the universe, from the near vacuum of intergalactic space containing less than 1 atom per cubic meter, through the varied densities of planets, stars, and stellar remnants, to the extreme densities of neutron stars and the singularities within black holes, density varies by factors of hundreds of billions of billions. These variations reflect the different conditions under which matter exists. The temperatures, pressures, compositions, and quantum mechanical states that determine how tightly matter can be packed together, creating the extraordinary range of cosmic objects we observe each with its own characteristic density, telling the story of how it formed and what forces shape its structure. Why some asteroids are made of metal? Most asteroids are dark, rocky bodies composed of silicate minerals similar to the rocks found on Earth's surface. But among the hundreds of thousands of asteroids orbiting in the main belt between Mars and Jupiter, a small population stands out as fundamentally different. These are the metallic asteroids, composed primarily of iron and nickel rather than rock. They gleam brightly in reflected sunlight, their surfaces shining with the luster of exposed metal. The most famous of these is Psyche, a massive asteroid about 226 kilometers in diameter that appears to be almost entirely metallic. Understanding why some asteroids are made of metal means understanding the violent history of the early solar system and the process by which planets form their layered structures of core, mantle, and crust. The story of metallic asteroids begins with planetary differentiation, the process by which a planetary body separates into layers based on density. When a planet or large asteroid forms, it starts as a mixture of materials, rock-forming elements like silicon, oxygen, magnesium, and calcium mixed with metallic elements like iron and nickel. If the body grows large enough and contains enough radioactive elements, it heats up from the decay of radioactive isotopes and from the energy of continued impacts as it accretes more material. When the temperature rises above the melting point of iron, about 1538 degrees Celsius, something dramatic happens. The iron, being denser than the surrounding silicate rock, begins to sink toward the center of the body. This process, called the iron catastrophe, releases enormous amounts of gravitational potential energy as the dense metal falls inward, further heating the body. The result is a differentiated structure with a dense iron-nickel core at the center, surrounded by a rocky mantle of lighter silicate minerals, and potentially a thin crust at the surface. This is the same basic structure that Earth possesses, an iron-nickel core containing about 32% of Earth's mass, surrounded by a silicate mantle and crust. Planetary differentiation occurred in the early solar system in bodies large enough to melt their interiors. Earth differentiated, Mars differentiated, Venus almost certainly differentiated. Even some large asteroids, like Vesta, which has a diameter of about 525 kilometers, underwent differentiation. Vesta has a basaltic crust formed from volcanic activity, indicating that it once had a molten interior with a metallic core. The asteroid Ceres, the largest object in the asteroid belt, at about 940 kilometers in diameter, shows evidence of differentiation as well. Once a body has differentiated into core, mantle, and crust, it becomes vulnerable to catastrophic disruption. The early solar system was a chaotic place, filled with planetesimals, asteroid-sized objects, colliding frequently as they orbited the young sun. Computer simulations of this period show that collisions were not just common, but inevitable. Some collisions led to accretion, with two bodies merging to form a larger one, but others were catastrophically disruptive, shattering one or both bodies into fragments. When a differentiated planetesimal is shattered by a sufficiently energetic collision, the fragments don't all have the same composition. Pieces from the core are metallic, pieces from the mantle are rocky, pieces from the crust might be volcanic basalts if the body had volcanism. These fragments become separate asteroids, each one representing a sample of a specific layer from the parent body. This is why we find three distinct types of asteroids in the main belt. C-type asteroids, which are carbonaceous and primitive, never having melted. S-type asteroids, which are stony and represent crustal and mantle material. And M-type asteroids, which are metallic and represent exposed cores. The M-type designation comes from their metallic composition, though determining composition from Earth requires spectroscopic analysis and radar observations. M-type asteroids are typically much more reflective than rocky asteroids. Their albedo, or reflectivity, ranges from about 10 to 18%, compared to 3 to 7% for dark carbonaceous asteroids. This high reflectivity occurs because metal reflects light efficiently compared to dark silicate minerals. The spectroscopic signatures of M-type asteroids show features consistent with iron and nickel, though definitively confirming their composition requires spacecraft missions or detailed radar studies. Radar observations provide particularly strong evidence for the metallic nature of M-type asteroids. Radio waves reflect differently from metal surfaces than from rocky surfaces. Metal is a much better radar reflector, and radar polarization measurements can distinguish metallic from rocky compositions. Studies using the Arecibo Observatory and Goldstone Solar System radar have confirmed that many M-type asteroids have radar properties consistent with metallic surfaces, supporting the interpretation that they're exposed planetary cores. The asteroid Psyche represents the most studied example of a metallic asteroid and the target of NASA's Psyche mission, launched in 2023 and scheduled to arrive at the asteroid in 2029. Psyche is unusual even among M-type asteroids because of its enormous size and apparently high metal content. If Psyche is indeed the exposed core of a differentiated planetesimal, it would be the only core of a planetary body that humans have ever been able to study directly. Earth's core lies 2,900 kilometers beneath the surface, completely inaccessible. Mars's core is similarly hidden, but Psyche's core is exposed, available for investigation. The composition of metallic asteroids reflects the composition of planetary cores more generally. Iron and nickel are the dominant elements, present in roughly the same proportions found in iron meteorites that fall to Earth, about 90% iron and 10% nickel, though with some variation. These proportions match what cosmochemical models predict for the cores of terrestrial planets. Additional elements found in smaller quantities include cobalt, phosphorus, sulfur, and carbon. Some models suggest that planetary cores might contain significant amounts of lighter elements, like silicon or oxygen, dissolved in the molten metal, but whether these would be retained in a fragmented, solidified core like Psyche remains uncertain. The value of metallic asteroids extends beyond scientific interest. These asteroids contain enormous quantities of valuable metals. A single metallic asteroid a kilometer across might contain more platinum group metals than have ever been mined on Earth. The asteroid 16 Psyche, if it's as metallic as estimates suggest, would contain iron alone worth quadrillions of dollars at current prices. Though of course, actually mining and returning such quantities would crash commodity markets and is far beyond current technological capabilities. Nevertheless, the concept of asteroid mining has captured imaginations and may become economically viable in the future as space access costs decrease and in-space manufacturing develops. Not all M-type asteroids are metallic, which complicates the picture. Some asteroids classified as M-type, based on their reflectivity and spectroscopic properties, might actually be enstatite chondrites, a rare type of rocky meteorites with high reflectivity, or other unusual rock types that mimic the appearance of metal. This demonstrates the difficulty of determining asteroid composition remotely. Only with spacecraft missions, sample return, or eventually human exploration can we definitively establish what these objects are made of. The formation of metallic asteroids also constrains the timing and locations of planet formation in the early solar system. Differentiation requires heating, which comes primarily from radioactive decay of short-lived isotopes like aluminum-26, which has a half-life of only 717,000 years. For aluminum-26 to provide significant heating, the planetesimal must form within a few million years of the solar system's birth, while aluminum-26 is still abundant. This timing constraint suggests that the parent bodies of metallic asteroids formed quickly, within the first few million years of solar system history. The subsequent disruption of these differentiated bodies likely occurred during a period of intense bombardment, possibly associated with dynamical instabilities in the giant planet's orbits. The Nice model, named after the city in France where it was developed, proposes that Jupiter, Saturn, Uranus, and Neptune formed in a more compact configuration and later migrated to their current orbits. This migration scattered planetesimals throughout the solar system, dramatically increasing collision rates and leading to the disruption of many differentiated bodies. The timing of this instability, estimated at around 600 to 800 million years after the solar system formed, would have been late enough for the large planetesimals to have already cooled and solidified after their differentiation. Iron meteorites that fall to Earth are fragments of metallic asteroids, providing samples we can study in laboratories. These meteorites show distinctive crystalline structures called Widmanstätten patterns, interlocking crystals of two different iron-nickel alloys, camosite and taenite, that form only when molten metal cools extremely slowly over millions of years. The size and structure of these crystals reveal the cooling history of the parent body's core. Some iron meteorites cooled at rates of only a few degrees Celsius per million years, consistent with cooling in the interior of a body tens to hundreds of kilometers in diameter, exactly the size of the differentiated planetesimals that became the parent bodies of metallic asteroids. The Widmanstätten patterns become visible when iron meteorites are cut, polished and etched with acid. The two iron-nickel alloys etch at different rates, revealing the crystalline structure. These patterns are beautiful and distinctive, and they can only form under the pressure and temperature conditions found deep within planetary cores, providing strong evidence that iron meteorites, and by extension metallic asteroids, genuinely represent fragments of ancient planetary cores. The distribution of metallic asteroids in the asteroid belt provides additional clues about the formation and evolution of the solar system. M-type asteroids are found throughout the main belt, but are somewhat more common in the middle regions. This distribution might reflect where conditions were favourable for forming large, differentiated planetesimals and where subsequent collisions occurred that could disrupt them. The relative scarcity of metallic asteroids compared to rocky ones, M-types represent only about 5 to 10% of asteroids, makes sense given that a differentiated body's core contains much less volume than its mantle and crust combined. Some metallic asteroids might not be fragments of differentiated bodies at all, but could have formed through different processes. Certain types of impactors, if they struck at very high velocities, could strip away a body's mantle and crust while leaving the core relatively intact. Alternatively, some metal-rich asteroids might have formed from material that was already enriched in metals during the solar system's formation, though this seems less likely given what we know about how materials were distributed in the protoplanetary disk. The Psyche mission will answer many questions about metallic asteroids when it arrives at its target. The spacecraft will map Psyche's surface in detail, measure its gravity field to determine how mass is distributed internally, study its magnetic properties to search for evidence of an ancient magnetic field that might have existed when the core was still molten, and analyze its composition using spectrometers and cameras. These measurements will reveal whether Psyche is indeed a nearly pure metallic core, as many scientists suspect, or whether it has a more complex structure with rock mixed in or covering parts of the surface. Understanding metallic asteroids means understanding planetary cores, the process of differentiation, the violence of the early solar system, and the building blocks from which planets formed. Every metallic asteroid is a window into planetary interiors, exposing material that would otherwise remain forever hidden beneath thousands of kilometers of rock. These fragments of ancient cores forged in the heat of differentiation and revealed by catastrophic collisions, represents some of the oldest processed materials in the solar system. Samples of the massive bodies that either grew into planets or were destroyed in the chaos of planetary formation, leaving behind their metallic hearts orbiting the Sun as testament to the violent processes that shaped our cosmic neighbourhood billions of years ago. Why moons orbit in perfect circles? When you look at diagrams of moons orbiting planets, they're often depicted as perfect circles with the planet at the centre. This image is actually misleading. No moon orbits in a perfect circle. Every orbit in the universe, whether it's a moon around a planet around a star, or a star around a galaxy's centre, follows an ellipse, a stretched circle with the central body at one of the ellipse's two focal points, not at the centre. However, many moon orbits are remarkably close to circular, so nearly circular, that the deviation is barely noticeable. Understanding why some moons have nearly circular orbits, while others follow elongated ellipses, means understanding orbital mechanics, tidal forces, and the long-term evolution of gravitational systems. The fundamental laws governing orbital motion were discovered by Johannes Kepler in the early 17th century, based on meticulous observations of planetary positions compiled by Tycho Brahe. Kepler's first law states that planets orbit the Sun in ellipses, with the Sun at one focus. This applies equally to moons orbiting planets. An ellipse is characterized by its eccentricity, a number between 0 and 1. An eccentricity of 0 represents a perfect circle. An eccentricity close to 0 represents a nearly circular ellipse. Higher eccentricities produce more elongated ellipses, and an eccentricity of 1 represents a parabola, an open curve, not a closed orbit at all. Earth's moon has an orbital eccentricity of about 0.0549, meaning its orbit is quite close to circular but noticeably elliptical. At its closest approach, called perigee, the moon is about 363,000 kilometers from Earth. At its farthest point, called apogee, it's about 405,000 kilometers away, a difference of about 42,000 kilometers, or roughly 11%. This variation causes the moon's apparent size in Earth's sky to change noticeably over the course of a month. A full moon at perigee appears about 14% larger in diameter than a full moon at apogee, the so-called supermoon phenomenon. Many other moons have far more circular orbits than Earth's moon. Jupiter's major moons, the Galilean satellites Io, Europa, Ganymede, and Callisto, all have very low eccentricities. Io's eccentricity is about 0.0041, Europa's is 0.009, Ganymede's is 0.0013, and Callisto's is 0.0074. These are remarkably circular orbits, with the differences between closest and farthest approaches being only tiny fractions of the orbital radius. Saturn's largest moon, Titan, has an eccentricity of 0.0288, still quite circular, though less so than Jupiter's major moons. The reason many moons approach circular orbits lies in tidal forces and the dissipation of energy over time. When a moon orbits a planet on an elliptical path, its distance from the planet changes continuously. As the distance changes, so does the strength of the tidal forces between the planet and moon. Tides work both ways. The moon raises tides on the planet, and the planet raises tides on the moon. These tidal bulges require energy to create because they deform the bodies involved, flexing and stretching them. For a moon in an eccentric orbit, the tidal bulges change in size as the moon moves closer to and farther from the planet. This continuous flexing dissipates energy as heat through internal friction, the same mechanism that makes a rubber ball warm up when you repeatedly squeeze and release it. This tidal heating is not a small effect. Jupiter's moon, Io, experiences such intense tidal heating due to its slightly eccentric orbit that it's the most volcanically active body in the solar system, with lava lakes, erupting volcanoes, and a surface constantly renewed by volcanic activity. The energy dissipated through tidal heating doesn't disappear. It comes from the orbital energy of the Moon. As orbital energy is lost, the characteristics of the orbit change. Specifically, the eccentricity decreases. The orbit becomes more circular. This process, called tidal circularization, operates on timescales of millions to billions of years, gradually transforming elliptical orbits into nearly circular ones. The timescale depends on the masses involved, the distances, the physical properties of the bodies, how easily they deform, and the initial eccentricity. Earth's moon provides a clear example of tidal evolution, though in the moon's case the effect is primarily in the exchange of angular momentum rather than circularization. The moon raises tides on Earth, the familiar ocean tides that rise and fall twice daily. Earth's rotation carries these tidal bulges slightly ahead of the Earth-Moon line because of friction and the time it takes for water to respond to the tidal forces. This offset means the tidal bulges pull on the moon, accelerating it in its orbit and causing it to gradually move away from Earth at about 3.8 centimeters per year, a rate precisely measured by bouncing laser beams of retroreflectors left on the moon by Apollo astronauts. As the moon moves outward, Earth's rotation slows down to conserve angular momentum. Earth's day gradually lengthens, currently by about 1.7 milliseconds per century. This process has been operating for billions of years. Early in Earth's history, when the moon was much closer, tidal forces were far stronger. Days were much shorter, perhaps only 5 to 6 hours, and the moon orbited much faster and on a more eccentric orbit. Over billions of years, tidal forces circularized the moon's orbit to its current low, but non-zero eccentricity. The moon's orbital eccentricity isn't zero because the circularization process hasn't completed and perhaps never will. The sun's gravitational pull perturbs the moon's orbit, periodically increasing its eccentricity slightly. These perturbations compete with the tidal circularization, creating a balance that maintains a small but non-zero eccentricity. Additionally, the ultimate end state of tidal evolution is tidal locking, where the moon always shows the same face to the planet, and the planet's rotation period equals the moon's orbital period. Earth's moon is already tidally locked to Earth, but Earth is not locked to the moon. Eventually, if given enough time, Earth would become locked to the moon as well, with both bodies always showing the same faces to each other, though this would take tens of billions of years, longer than the sun's remaining lifetime. Some moons maintain eccentric orbits despite tidal forces because of orbital resonances with other moons. Jupiter's moons Io, Europa, and Ganymede are locked in a 1 to 2 to 4 resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This resonance was discovered by Pierre-Simon Laplace in the 18th century. The gravitational interactions in this resonance maintain Io's and Europa's orbital eccentricities even as tidal forces try to circularize them. The result is continuous tidal heating, keeping Io's interior molten and likely maintaining a subsurface ocean on Europa beneath its icy crust. Saturn's moon, Enceladus, experiences similar effects. Its orbital eccentricity of about 0.0047 seems small, but it's sufficient to generate significant tidal heating in this small moon. Enceladus orbits in a 2-to-1 resonance with the larger moon Dione. The resonance prevents the orbit from fully circularizing, maintaining just enough eccentricity to produce tidal heating that keeps a subsurface ocean liquid beneath Enceladus's southern polar region. Geysers of water erupt through cracks in the ice, spraying material into space and creating Saturn's E-ring. New moons in eccentric orbits take time to circularize. If a moon forms from a giant impact, as Earth's moon likely did, the debris initially orbits in highly eccentric, chaotic paths. Over time, collisions between orbiting fragments dissipate energy and circularize the orbits, while material gradually coalesces into a single moon. The moon starts with a moderately eccentric orbit that gradually becomes more circular through tidal interactions. Young moons should have more eccentric orbits than old moons, all else being equal. Captured moons often retain eccentric orbits. When a planet gravitationally captures a passing asteroid or comet, the capture typically results in a highly eccentric orbit. Without significant tidal forces or atmospheric drag to circularize the orbit, it remains eccentric indefinitely. This is why many of the small, irregular outer moons of the giant planets have highly eccentric orbits. They're captured asteroids, or Kuiper belt objects, that have never undergone significant tidal circularization. Mars's two small moons, Phobos and Deimos, are thought to be captured asteroids, though their orbits are fairly circular, suggesting either that they've been in place long enough for tides to act or that they were captured through an unusual mechanism that placed them in nearly circular orbits initially. The mathematical framework for understanding orbital evolution through tides was developed in the 19th and 20th centuries by George Darwin, son of Charles Darwin, and others. The tidal quality factor, denoted Q, quantifies how efficiently a body dissipates tidal energy. Bodies with low Q dissipate energy efficiently, leading to faster orbital evolution. Rocky bodies typically have Q values of 10 to 100. Gas giants have Q values around 10,000 to 100,000 because gases don't maintain permanent tidal bulges as efficiently as solid or liquid bodies. These Q values determine how quickly orbits evolve. Computer simulations of moon system evolution incorporate tidal effects, gravitational interactions between multiple moons, and perturbations from the Sun and other planets. These simulations show that systems naturally evolve toward configurations with circular orbits, tidal locking, and often orbital resonances. The solar system's moon systems we observe today represent billions of years of this evolution, with orbits that have circularized, resonances that have captured moons into stable configurations, and tidal locking that has synchronized rotations. Some moons will never fully circularize their orbits because external perturbations constantly act to increase eccentricity. The moon's orbit around Earth is perturbed by the Sun, creating periodic variations in eccentricity over 27.5-day cycles. Neptune's moon Triton orbits in a retrograde direction, opposite to Neptune's rotation, suggesting it was captured from the Kuiper belt. Triton's orbit has circularized over billions of years to an eccentricity of only 0.000016, one of the most circular orbits known, but the orbit is also slowly decaying. Tidal forces are causing Triton to spiral inward, and in about 3.6 billion years, it will cross Neptune's Roche limit and be torn apart, forming a spectacular ring system. The appearance of circular orbits in diagrams and popular depictions stems from the fact that many major moons genuinely have nearly circular orbits. Eccentricities low enough that drawing the ellipse versus a circle would show barely any difference. For Ganymede, with its eccentricity of 0.0013, the difference between the orbit's longest and shortest diameters is only 0.26%. Drawing this accurately would require extraordinary precision. For practical purposes, these orbits are functionally circular, even though they're technically ellipses. Perfect circles don't exist in orbital mechanics because achieving exactly zero eccentricity requires perfectly balanced initial conditions and no subsequent perturbations. Conditions that never occur in nature. But through billions of years of tidal evolution, many moons have achieved orbits so close to circular that they serve as excellent approximations shaped by the patient, inexorable work of tidal forces, dissipating energy, transforming the chaos of formation into the elegant, nearly circular orbits that characterize mature moon systems throughout the solar system, demonstrating how gravitational interactions over immense timescales can organize and simplify what begins as disorder, creating the stable, predictable, celestial mechanics that allow us to calculate moon positions years or centuries into the future with extraordinary precision. Where baby stars come from. Stars are not born in the bright, empty spaces between galaxies or in the clear voids of interstellar space. They emerge from darkness, from vast clouds of gas and dust that hang in the spiral arms of galaxies, regions so dense with obscuring material that they appear as black patches against the glowing background of the Milky Way. These stellar nurseries, called molecular clouds, are the cosmic wombs where stars begin their lives, places where gravity, temperature, pressure, and chemistry conspire to transform diffuse gas into brilliant spheres of nuclear fusion that will shine for millions or billions of years. The process begins with a molecular cloud, an enormous accumulation of gas and dust drifting through the galaxy. These clouds are cold, typically only 10 to 20 degrees above absolute zero, and they're composed primarily of molecular hydrogen, two hydrogen atoms bonded together, mixed with helium and trace amounts of heavier elements. The clouds also contain dust grains, tiny particles of silicates and carbon compounds, each grain smaller than a bacterium, but collectively making up about 1% of the cloud's mass. These dust grains play a crucial role despite their small mass contribution, shielding the interior of the cloud from starlight and cosmic rays, allowing it to remain cold enough for molecules to survive. Molecular clouds range in size from relatively small clouds, a few light years across, to giant molecular cloud complexes spanning hundreds of light years and containing enough material to form hundreds of thousands of stars. The Orion Molecular Cloud Complex, one of the nearest star-forming regions at about 1,300 light-years from Earth, contains enough gas to make roughly 100,000 stars, like the Sun. The cloud extends across much of the constellation Orion, with the famous Orion Nebula marking just one small region where star formation is particularly active and visible. For stars to form, something must disturb these clouds, compressing them beyond a critical threshold where gravity overwhelms the internal pressure that normally keeps the cloud stable. This compression can come from several sources. A shockwave from a supernova explosion, traveling through space at thousands of kilometers per second, can slam into a molecular cloud and compress it. The spiral density waves that create the spiral arms of galaxies compress gas as it enters these regions, triggering star formation that lights up the spiral arms with young, bright stars. Even the radiation and stellar winds from existing massive stars can compress surrounding gas, triggering new generations of star formation in a process that propagates through the cloud. Once a region of the cloud is compressed, gravity takes control. The denser parts of the cloud pull in surrounding material, growing denser still. This runaway process would cause the entire cloud to collapse into one enormous star, but molecular clouds are turbulent places, filled with eddies and currents of gas flowing in different directions. This turbulence, combined with the cloud's rotation and magnetic fields threading through it, breaks the cloud into fragments. Each fragment, typically containing anywhere from a fraction of a solar mass to tens of solar masses, becomes the seed of a star or a small system of stars. As a fragment collapses, it heats up. This might seem counterintuitive. How does something heat up as it collapses in the cold of space? The answer lies in gravitational potential energy. As gas falls inward, it accelerates, gaining kinetic energy. When fast-moving atoms and molecules collide with other particles, they convert their kinetic energy into thermal energy, heat. The center of the collapsing fragment grows hotter and denser, while the outer regions continue to fall inward, feeding the growing concentration at the center. The collapse doesn't proceed smoothly or uniformly. The fragment rotates, inherited from the overall rotation of the molecular cloud, and conservation of angular momentum means it spins faster as it shrinks, just as an ice skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the center. Instead, material settles into a rotating disk around the growing protostar, the nascent star at the center. This disk, called a protoplanetary disk or protostellar disk, channels material toward the protostar, while the outer parts remain in orbit, eventually becoming the raw material from which planets might form. The young protostar, deeply embedded in the infalling gas and dust, is invisible at optical wavelengths. The surrounding cocoon of material absorbs any visible light the protostar emits and re-radiates it as infrared radiation. This is why infrared telescopes are essential for studying star formation. They can penetrate the dust and observe the protostars hidden within molecular clouds. The Spitzer Space Telescope and now the James Webb Space Telescope have revealed thousands of these embedded protostars, showing snapshots of stars at various stages of formation. As the protostar continues to accrete mass, its central temperature and pressure climb steadily. The journey from cold molecular gas to a hot protostar takes roughly 100,000 years for a Sun-like star, though this timescale varies depending on the protostar's mass. More massive protostars collapse more quickly because their stronger gravity accelerates the infall. Less massive protostars take longer, sometimes millions of years, to fully form. The protostar doesn't simply accrete all the material that falls towards it. Young protostars are violent, magnetically active objects. Magnetic field lines threading through the protostar, and its disk can become twisted and tangled by the rotation. And these magnetic fields launch jets, narrow beams of gas that shoot outward from the protostar's poles at speeds of hundreds of kilometers per second. These jets are one of the most distinctive signs of active star formation. The Hubble Space Telescope has captured stunning images of these jets, often light years long, streaming away from young stars still hidden within their dusty cocoons. The jets serve an important function. They carry away angular momentum and energy that would otherwise prevent further accretion. Without some mechanism to remove angular momentum, the disk would simply spin faster and faster, and material would stop falling onto the protostar. The jets, along with stellar winds, outflows of gas from the protostar's surface, solve this problem, allowing the protostar to continue growing even as it spins. Where the jets slam into the surrounding molecular cloud, they create glowing knots and filaments called Herbig-Haro objects, named after astronomers George Herbig and Guillermo Haro, who studied them in the 1950s. These objects glow because the jet's high-speed collision with the ambient gas heats it to thousands of degrees, causing atoms to emit light. Herbig-Haro objects can move visibly over timescales of years, and they serve as signposts marking regions of active star formation. The accretion phase lasts for roughly 1 million years, though again this varies with stellar mass. During this time, the protostar is not yet a true star because no nuclear fusion occurs in its core. It shines from gravitational energy. The energy released as material falls onto its surface, and as it slowly contracts under its own weight. This contraction, described by Hermann von Helmholtz and Lord Kelvin in the 19th century, heats the interior gradually. Eventually, after millions of years of contraction and heating, the core temperature reaches approximately 10 million degrees Celsius. At this critical temperature, protons moving at extremely high speeds collide with enough energy to overcome their mutual electrical repulsion and fuse together, creating helium and releasing energy. This ignition of hydrogen fusion marks the birth of a true star. The protostar becomes a main sequence star, entering a stable phase where the energy released by fusion creates outward pressure that balances gravity's inward pull. For a star like the Sun, This moment arrives roughly 10 million years after the initial collapse began. The newly formed star is now generating its own energy through nuclear reactions rather than relying on gravitational contraction. It will remain on the main sequence, fusing hydrogen in its core for about 10 billion years, 100 times longer than it took to form. Not all fragments in a molecular cloud form single stars. Many form binary or multiple star systems where two or more stars orbit each other. The fragmentation process can produce two separate cores within a single disk, each growing into a star. Or a protostellar disk can become gravitationally unstable and fragment, forming additional stars. About half of all stars exist in binary or multiple systems, making our single sun somewhat unusual. The smallest fragments don't have enough mass to ever ignite hydrogen fusion. Objects below, about 0.08 solar masses, roughly 80 times Jupiter's mass, never reach core temperatures high enough for hydrogen fusion. These failed stars, called brown dwarfs, glow dimly from their residual heat and from the fusion of deuterium, a heavy isotope of hydrogen that fuses at lower temperatures than normal hydrogen. Brown dwarfs slowly cool over billions of years, gradually fading from view. The most massive fragments form massive stars, objects with tens of times the Sun's mass. These stars form quickly, sometimes in just a few 100,000 years, and burn brilliantly but briefly. They produce intense ultraviolet radiation that ionizes the surrounding gas, creating glowing H2 regions like the Orion Nebula. The radiation pressure from these massive stars is so strong that it can halt further star formation nearby, blowing away the remaining gas and effectively shutting down the stellar nursery. The wind and radiation from massive young stars create expanding bubbles in the molecular cloud, clearing out regions and compressing gas at the bubble's edges. This compression can trigger new star formation, creating generations of stars, with the oldest stars at the center and progressively younger stars toward the periphery. The entire process is self-propagating until the molecular cloud is either dispersed entirely or exhausted of dense gas. When the most massive stars explode as supernovae after just a few million years, they inject tremendous energy into their surroundings, heating and dispersing the remaining molecular cloud and enriching it with heavy elements created in the star and in the explosion. The shockwave from the supernova can compress nearby clouds, triggering new rounds of star formation. In this way, star formation is a cyclical process. Stars form from clouds, massive stars disrupt clouds, supernova shockwaves compress new clouds, and stars form again. The entire life cycle from molecular cloud to dispersed star cluster takes roughly 10 to 20 million years. The Orion Nebula, one of the most famous star-forming regions visible to the naked eye, contains stars that are only about 1 to 2 million years old, cosmic newborns still surrounded by the glowing remnants of the cloud that birthed them. Over the next few million years, the radiation from these young stars will disperse the remaining gas, leaving behind a star cluster that will gradually spread apart as its members drift through the galaxy. Understanding where baby stars come from means understanding one of the fundamental cycles of the cosmos. The gas from which stars form was once inside previous generations of stars. Those stars fused hydrogen into helium, helium into carbon and oxygen, and heavier elements still, then returned that enriched material to space through stellar winds and supernova explosions. That material mixed into molecular clouds and became incorporated into new stars, including our Sun, which formed about 4.6 billion years ago from a molecular cloud that contained the ashes of earlier stellar generations. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in stars that formed, lived, died, and seeded the molecular cloud from which the Sun and Earth eventually emerged, continuing the ancient cycle of stellar birth and death that has shaped the galaxy since stars first began forming over 13 billion years ago. Why alien life might be microscopic. When we imagine alien life, our minds often conjure images of intelligent beings piloting spacecraft, complex organisms with eyes and limbs exploring alien landscapes, or at minimum, creatures we could observe and recognize as alive. But this expectation might be profoundly misguided. Earth's history offers a sobering perspective. For roughly 3 billion of the 4 billion years that life has existed on our planet, all organisms were microscopic. Bacteria, archaea, and single-celled eukaryotes dominated Earth's biosphere for the vast majority of life's history. Complex multicellular organisms, plants, animals, fungi, are recent arrivals, having existed for less than 1 billion years. If Earth's timeline is any indication, most life in the universe might be microscopic, existing as single cells or simple colonies that never evolve into the complex macroscopic forms we're accustomed to seeing. The transition from single-cell to multicellular life represents one of the most difficult evolutionary innovations in Earth's history. It only happened once in the bacterial lineage, never successfully transitioning beyond simple filaments and colonies, and only a few times in the eukaryotic lineage, producing plants, animals, and fungi. This rarity suggests that while single-celled life might emerge relatively easily wherever conditions permit, the evolution of complex multicellularity requires specific circumstances that might not commonly occur. Many alien worlds might develop thriving microbial biospheres that remain forever microscopic because the evolutionary innovations needed for large, complex organisms never occur. Energy availability represents the first major constraint on complexity. Complex multicellular organisms require substantial energy to build and maintain their bodies. They need energy to power specialized organs, to move through their environments, to grow to large sizes. Most of this energy ultimately comes from oxygen-based metabolism, which releases far more energy per molecule of food than anaerobic metabolism does. The efficiency of oxygen metabolism, about 15 times more energetic than the best anaerobic alternatives, enabled the evolution of large active organisms on Earth. But oxygen was not always available in Earth's atmosphere. For the first 2 billion years or more of life's existence, the atmosphere contained very little free oxygen. Life during this time remained entirely microscopic and relatively simple, constrained by the low energy yields of anaerobic metabolism. Only after photosynthetic bacteria evolved and began producing oxygen as a waste product did atmospheric oxygen accumulate, and only after oxygen reached substantial levels could organisms evolve the high-energy metabolisms necessary for large size and complexity. Many alien worlds might never undergo this transition. If photosynthetic life never evolves, or if it evolves but produces different waste products, perhaps using electron donors other than water that don't release oxygen, the atmosphere might remain oxygen poor indefinitely. Life on such worlds would be permanently restricted to anaerobic metabolism, with its inherent energy limitations preventing the evolution of large complex organisms. The biosphere might flourish with countless microscopic species filling every available niche, but nothing larger than perhaps a millimeter would ever evolve, because the energy budgets of anaerobic metabolism cannot support larger sizes or more complex structures. Predation drives much of the evolution toward complexity on Earth. The development of predators created selection pressure for prey to evolve defenses, armor, toxins, multicellularity that makes them too large to be consumed by single-celled predators. Predators, in turn, evolved mechanisms to overcome these defenses: better sensing systems, faster movement, cooperative hunting. This evolutionary arms race between predators and prey drove increasing complexity, with both sides becoming more sophisticated over generations. The transition to multicellularity in animals might have been driven at least partially by predation pressure from other single-celled organisms. On an alien world where predation never becomes significant, perhaps because environmental conditions don't favor the evolution of heterotrophs, or because chemical energy is so abundant that organisms don't need to consume each other, this driver of complexity would be absent. Life might remain a collection of bacteria-like organisms metabolizing chemicals from their environment, with no selection pressure favoring the evolution of larger, more complex forms. Without predation or competition driving an evolutionary arms race, the biosphere might reach an equilibrium of simple, efficient microorganisms that persist unchanged for billions of years. The evolution of eukaryotic cells, cells with nuclei and complex internal structures, required an extraordinarily unlikely event called endosymbiosis, where one cell engulfed another and instead of digesting it, established a permanent symbiotic relationship. On Earth, mitochondria, the energy-producing organelles in eukaryotic cells, originated as free-living bacteria that were engulfed by other cells and eventually became integrated parts of those cells. This event, which happened roughly 2 billion years ago, was apparently unique in Earth's history. It happened once, and all eukaryotic cells descend from that single event. Eukaryotic cells made complex multicellular life possible. Their mitochondria provide far more energy per cell than bacteria can generate, allowing cells to support larger genomes and more complex structures. Their internal compartmentalization allows specialized biochemistry to occur in different cellular regions. Their complex cytoskeletons enable intricate cell shapes and coordinated movements. Without eukaryotic cells, complex multicellular organisms probably could not evolve. If endosymbiosis was difficult, requiring very specific circumstances to occur even once on Earth, alien worlds might never undergo this transition. Life might remain forever bacterial, lacking the cellular complexity necessary as a foundation for multicellular organisms. These worlds would have rich microbial ecosystems with tremendous diversity at the microscopic level, but would never produce organisms visible to the naked eye. Environmental stability influences evolutionary innovation. Earth's environment has been highly variable over geological time. Ice ages, warming periods, asteroid impacts, volcanic catastrophes, changing atmospheric composition, continents drifting and colliding. These environmental changes created selection pressures that favored adaptability and innovation. Mass extinctions wiped out dominant groups, allowing new forms to radiate and diversify. Without such disruptions, dominant organisms might remain unchanged indefinitely, never facing circumstances that favor more complex alternatives. An alien world with a remarkably stable climate and environment over billions of years might never see complex life evolve. Early microbial ecosystems might reach an equilibrium where existing organisms are so well adapted to unchanging conditions that no complex innovations provided advantages. Microbes would efficiently fill every niche, processing every available chemical, extracting every erg of available energy, and no evolutionary pressure would favor the metabolically expensive transition to larger, more complex forms. The planet would remain microbial forever, not because complex life is impossible, but because stable conditions never create circumstances where complexity is advantageous. The availability of ecological niches affects diversification. On Earth, new environmental niches continuously opened as continents drifted, climates changed, and oxygen accumulated in the atmosphere. Moving onto land created entirely new sets of niches, terrestrial environments with different challenges than aquatic ones. Flying created another set of niches. Each new opportunity drove adaptive radiations where organisms evolved to exploit newly available resources and habitats. A planet lacking this niche diversity might not provide opportunities for complex life to evolve. A world completely covered by ocean, with no land, would lack terrestrial niches. A world with a homogeneous environment, perhaps a global ocean, with uniform temperature and chemistry from pole to pole, would offer fewer distinct niches than Earth's highly varied environments. With fewer niches available, there would be less opportunity for adaptive radiation and less selection pressure driving organisms toward the specializations and complexities that fill diverse ecological roles. Timescales matter significantly. Evolution proceeds through random mutations and natural selection, accumulating beneficial changes over countless generations. Complex innovations require many individual evolutionary steps, each one building on previous changes. The evolution of eyes, for instance, required the initial evolution of light-sensitive proteins, then the gathering of these proteins into light-sensitive patches, then the invagination of these patches into cups that provide directional information, then the development of lenses that focus light, then the neural processing systems to interpret visual information. Each step took many generations and many mutations. On an alien world where organisms have very long generation times, perhaps living for thousands of years before reproducing, evolution would proceed extraordinarily slowly. A complex innovation that might evolve in tens of millions of years on Earth, where many organisms reproduce annually or even faster, might take billions of years on a world where generation times are measured in millennia. If the planet star has a relatively short lifetime, perhaps a massive star that will exhaust its fuel in a few billion years, there might simply not be enough time for complex life to evolve before the star's death sterilizes the planet. The chemical environment limits biological complexity. Complex organisms require diverse biochemistry, proteins for structure and catalysis, lipids for membranes, nucleic acids for information storage, carbohydrates for energy and structure. Building these diverse molecules requires access to various elements in appropriate forms. A planet poor in essential elements, perhaps lacking sufficient phosphorus, nitrogen, sulfur, or trace metals, might not provide the chemical building blocks necessary for complex biochemistry. Life might arise using simpler chemistry, but might be unable to evolve the molecular diversity needed for complex cells and multicellular structures. Physical constraints on size affect what complexity is possible. Surface tension becomes increasingly important at small scales. For microscopic organisms living in water, surface tension is a significant force. Water behaves more like thick syrup than like the thin fluid humans experience. Moving through water at microscopic scales requires different strategies than swimming at macroscopic scales. These physical differences mean that microorganisms experience a fundamentally different physical world than large organisms, and the adaptations that work well at microscopic scales might not scale up successfully. The speed of light sets absolute limits on how quickly information can be transmitted within an organism. For microscopic cells, this is never a constraint. Signals cross the cell in negligible time. But as organisms grow larger, signal transmission times become significant. A 1-meter organism experiences light travel times of about 3 nanoseconds, still essentially instantaneous for chemical and neural signals. But organisms must coordinate their parts, and this coordination becomes more difficult as size increases. Neural signals in humans travel at speeds of about 100 meters per second, meaning signals take milliseconds to travel from extremities to brain. For a hypothetical organism many meters or kilometers in size, coordination would become increasingly difficult. Detection bias affects our perception of what life looks like. Humans evolved to perceive objects roughly our own size. We see animals, plants, and landscape features easily because our sensory systems are optimized for that scale. microscopic organisms are invisible without technological assistance. An alien observer visiting Earth equipped with sensing systems similar to human vision might conclude that Earth has relatively little life, missing entirely the vast microbial world that actually dominates in terms of biomass, diversity, and metabolic activity. Similarly, when we search for alien life, our methods tend to focus on detecting macroscopic effects, oxygen in atmospheres produced by photosynthetic organisms, changes in planetary albedo from vegetation, perhaps even artificial lights from technological civilizations. A planet covered in microbial life, producing no oxygen, with no multicellular organisms, with nothing visible at planetary scales, might appear lifeless to our telescopes, even if it hosts an incredibly rich and diverse microbial biosphere. Statistical considerations based on Earth's history suggest that if we discovered alien life, it would most likely be microscopic. Life existed on Earth for about 3 billion years before complex multicellular organisms evolved. If we randomly selected a moment in Earth's history, there would be a roughly 75% chance of finding only microscopic life. Assuming Earth's timeline is typical, which may or may not be true, most inhabited planets at any given time would be in their microbial phase, with complex life being relatively rare. Why alien life might be microscopic comes down to microbial life being easy to achieve relative to complex life, requiring only basic metabolism, reproduction, and evolution, while complex life requires numerous specific evolutionary innovations, oxygenic photosynthesis or equivalent high-energy metabolism, eukaryotic cells with their mitochondrial endosymbionts, multicellularity with coordinated cells working together, specialized tissues and organs, each one potentially rare or slow to evolve. Many worlds might develop thriving microbial ecosystems within their first billion years, but might never progress beyond that stage, remaining forever inhabited by bacteria-like organisms invisible to the naked eye, yet representing the most common form of life in the universe. A cosmos filled not with civilizations or even visible organisms, but with countless worlds hosting microbial biospheres that flourish in every conceivable environment, from sunlit surface waters to deep subsurface rocks, from hydrothermal vents to subsurface oceans beneath ice, each microscopic cell representing a success story of evolution in its own right, reminding us that complexity and large size are not prerequisites for biological success, and that if we ever detect life beyond Earth, we should not be disappointed if it consists of nothing more than microbes, because microbial life might be life's most common, most successful, most enduring form across the vast expanse of the living universe.